Hi, this is the Tempter podcast where we discuss embedded Linux, IoT development, and anything else we might find interesting. Your hosts today are Kim Raj and Cliff Brake. Hi, Kim.
Hey, Cliff. How are you doing today?
Yeah, pretty well. How about you?
Doing well, thank you.
Good. So today we want to talk about build acceleration and the various topics around that. And Kim has a lot of experience in build systems. So I guess the fundamental problem is builds are sometimes slow, and this is, we've seen build times for applications up over a half hour sometimes, at least I have personally. And of course, system builds, where we build the entire system, like in Yocto, on a slower machine, those can go for a good part of a day. On a fast machine, they're usually, I don't know, what do you say, Kim, an hour or something? Or what's your machine do?
Yeah, something like an hour.
Mm-hmm.
Less than an hour is lucky.
Yeah. So this is a big problem because when we develop, we want feedback, and if our builds are slow, then that slows down our feedback loop, which is the general problem we're trying to solve. So anyway, maybe we could start with why are builds slow?
Yeah. $1 million question. Builds actually, if you look back, people build software, everything in a monolith, right? So you build the whole thing together, and over a period of time, software has grown by leaps and bounds, and it has kept up to date with your hardware, in the sense that you basically have fast hardware, but then you have more software nowadays to build, right? So you have complex applications, huge platforms. So if you were to compare linear, a monolithic build to monolithic build, probably we aren't any much better than we were, say 10, 20 years ago. We are still spending the same amount of time.
Yeah, that's amazing that my computer is not much faster than my Commodore 64. Right. I mean, it is a lot better. I shouldn't say that, but the Commodore 64 was a perfectly usable machine. So
Yes, absolutely. So I think it's just that we are building more and we are building faster, but we are building a lot more too. So, So this eternal problem of build acceleration has been there, and it will always be there. It might morph into some other immediate challenge, but it still remains there, primarily because it impacts your productivity. So I think the most important time that you have is the human time, the programmer's time, or whoever is interacting with the system. That's time. Compute time is important, but it still is a machine time. It's a bit cheaper comparatively. So there is economy behind it, and there are other aspects that you mentioned where you really want a faster feedback. And the reason for that is also that you are basically focused on a problem, and if this is coming in your way, you are not being effective at that point. So a tighter loop definitely helps you concentrate, solve the problem. So to come back to your original question, why builds are slow. We have a ton of software to build. Now, really, what really matters is now how do you take this problem and then solve it by various methods, and that's the interesting part that I guess we can talk about.
Sure. So are pretty much all languages created equal, or do you feel that some languages tend more to slower builds than other languages? I know it's kind of a loaded question, but it's
yeah, it's a good one. So it's traditionally, as I mentioned, you had monolithic builds, and you built things in serial order to a certain extent, and you didn't have a lot more modularity, or at least you didn't do that for whatever reasons. And then, what some systems like Linux and maybe others did is they kind of made it modular. So I'm speaking from systems point of view. So they said you could build this library separately. You could build, certain pieces of your whole system separately. You can build the kernel separately, bootloader separately, and that was great. And essentially, it gives you, a bit of build acceleration if you look at that. So you put your Linux system together, and then you create a smaller loop for, say, you are a kernel developer, then you can iterate fast on just on the kernel piece. However, that works in certain scenarios, doesn't work in all scenarios. Secondly, the applications have become a lot bigger nowadays. So, that goes to the previous point where, kernel used to be the biggest component that you had in the system, and that may not be the case anymore if you look at, the apps that we have today, the browsers we have today, and not one, not two, but many.
Yeah, so, Chromium is huge and takes, you have to have like 32 gigabytes of memory in your machine, or maybe more, to even build it.
Yeah, more the merrier.
Yeah.
That's
so that has probably eclipsed the kernel in size and definitely in build time.
Yeah, absolutely. So
there's one thing I've been fairly impressed with the Linux kernel. It's a huge code base, millions and millions of lines of code, and it does build reasonably fast. It's they seem to have kind of kept a handle on that. And I'll relate one other experience I had in an application some years back we developed in C++. And the team wasn't necessarily as careful as we should have been about headers, who included what. And if you tend to be sloppy about that, you have headers that get included in everything, because headers include headers, and pretty soon, anytime you touch any module, the whole system rebuilds, and it took like a half an hour. So, that, I guess the one key to making builds fast is don't rebuild stuff you don't need to. And build systems help a lot with that, but you have to use them right, or especially in C and C++, you have to be careful with your includes.
Yeah.
And in general, I think it's probably a good idea to not have include multi-level of includes, because then it's very hard to understand what's going on. And I don't know if the Linux coding standards, I haven't worked there in a while, but if they have standards on that, like you don't have these global includes that just pull in everything. So it's a good question. I think one of the reasons why Linux has, relatively speaking, smaller build times given its size is, number one, I think it uses this cake and fake system. So you are essentially building a profile of a kernel, right? Most of the time, you're building a kernel for a particular device or machine. You're not enabling everything that's in there, although you might be doing that for various other reasons, but practically you may not be doing that. So essentially, build what you need, right? Sure.
So that's another thing to build once and use again, like use many times. So that's another mantra is like build what you need, and that is actually very true given the cake and fakes ability to nicely separate out features. It kind of gives you a very polished profile that you're building. The second thing it does good is the kernel modules. And at a certain point of time, the kernel modules are kind of an independent component within kernel, right? So it's like you're building shared libraries, and then you can do a lot more parallelism there, right? So you can basically go ahead and do a lot of parallel builds and your kernel can still stay smaller, which means your link time for the kernel will not go up, like it is for, say, WebKit or others, right, where you spend minutes in linking. In this case, you don't have to do that because, you're kind of like split it out into modules and nicely done that way, because then the programming model also is good because, if you're working on a kernel driver, it can be a kernel module, we're not bothered about kernel proper as much, right? So you can build that once and it can just kind of iterate over the kernel module faster. And that's awesome because I think, that as a developer, you are kind of in a kernel space, but within the kernel space, you are still in a module space. So, it's really amazing. You might be like working on 1 or 2 C files in there and then just iterating over that. So that's very, very powerful. And the other thing, I think you touched on the headers. So there was a report published by some Google engineers, I think some time ago. I don't have the reference right now, but it was about, build times for Chromium, the browser. And they figured out that, the 30%, I believe, maybe, plus and minus, of the time you do spend in build is in pre-processing, right? And the pre-processing is essentially basically a compiler bringing in all the headers that you're including and then what they are including and the whole tree, and then creating a single compilation unit, which is then compiled into a .o, the object file, right? So the compilation process, the first thing is basically pre-processing, which is basically just including the things, expanding, the macros, and that sort of stuff, and then creating this large pre-processed source file for that particular compilation unit. Now, if you're spending 30% of time, say if you didn't do any includes, right, everything, you would be like 30% faster just by doing that. Now, so you have to have, as you mentioned earlier, is you need to have some discipline about your headers and how you organize your declarations. And speaking of C++ here, and Chromium did show, the Chromium build analysis did show that there is a huge penalty you pay for doing the recursive includes, and not only the pre-processing part, but now because you're including so many headers, your compile unit is growing, right? And if your compile unit is growing, naturally your compile time will also go up because now the real compiler also has more work to do, even though a lot of that work may be thrown away by because it's unused code or stuff like that. But in the end, your compile time is very, is impacting all the way, right? So, kernel is actually, very careful about headers. So, I remember from my own personal experience where I submitted patches to include a compiler.h, and there were like questions asked. Oh, you're including a new header. Why, right? So a discipline that, is a review and an aware community, which is a blessing in disguise. Which kind of keeps you in check of saying, hey, I included that header, but I really needed to include like a macro, from the C library. And then you basically, you might have like all.h or something like that. I've seen some like proprietary projects where they have, certain super include files of that nature. Yeah. So you include that file in a source and everything is taken care of, right? But that is actually where the problem starts.
Exactly, right.
And it's important that you include what's needed and help the preprocessor, not gobbling too many bits that you really don't need. There are tools though now in Clang, which could basically give you some information about your include headers and things like that. So there are tools that you could use to kind of analyze your projects and find out these kind of scenarios. But once done, it's very hard to undo them, because you have to make sure that there was not unintended effect of that include that you're relying on. So sometimes.
Yeah,
You know,
if def really makes that a problem because it's not a compile error. It's just it behaves differently if this is not defined. So
yeah, absolutely.
Yeah, those are great points. So the first thing is you need to have discipline and start with a clean architecture.
Mm-hmm.
And like you said, if there's boundaries, natural boundaries in the system, that helps to keep things more contained and you don't have stuff leaking all over the place so that a small change here forces everything to rebuild over here. And that's just good architecture, is to have good API boundaries. So,
yeah, absolutely.
So as far as moving on from the basic discipline and structure of your code, what are some other technologies that you've seen in the C++ space that help us go faster?
Mm-hmm. Yeah, so I think there are certain tools that you can deploy, right? So one of the tools, or one of again the tools is use parallelism in your build, right? So a lot of times software is not buildable in parallel, right? Because they have build race conditions and
Mm-hmm.
something depending upon something, and so a fix is make minus J1, right? And what happens with that is nowadays, most of your computers are multi-core, right? So take advantage of that. So basically, one of the tools I would, immediately say is, hey, why can't we build it in parallel if you're not doing it, right? There has to be a reason that there is a serialization point. Then up to that serialization point, we can build everything in parallel and stuff like that. However, the other tools that have been around, especially in C++ world, are for caching. So we talked about pre-processing, and there's a tool called ccache. Ccache is basically caching some of your pre-processed objects and also your build objects. So making sure that if it's able to reuse them in your builds again, right? So ccache definitely helps with that. Now, it may have certain aspects of it that may not be very evident, but a lot of times I have seen packages fail when ccache is enabled for them, and you have to careful that this is another layer that you're adding into your build, mm-hmm. right? So as you layer more stuff, build becomes complex. So you are trading speed with complexity here. That's all I wanted to mention.
Sure, there are trade-offs. Yeah.
Yes. So it's not something that, here is a CMake. Let's enable the C cache underneath. So there is a penalty you pay. It's just not for free. And similarly, there was distc in the past, which kind of nowadays is ice cream, which is kind of a distributed compiler. So if you have a network of computers, you could basically distribute your parallel builds across in a distributed kind of a cluster sort of. This works fine if you in the past, because your disks were slow, you were not really bound by network. You are really bound by I/O, right, and compute. Then this is awesome, because then if you have slow computers sitting on somewhere, just kind of add them to your node, and they can do some of the work. So ICC basically distributes the build across all these nodes, sends the pre-processed objects, it gets compiled over there, brings it over, and then links it on your main system.
Mm-hmm.
Helps. But in modern days, I think, given you have SSDs and NVMe technologies, you're not really bound by disk anymore. So unless you have ultra fast, backend network,
yeah,
400 gigabits per second or something, some crazy amount. this may not scale,
Mm-hmm.
into. But if you have like your home kind of setup, it might be fine because you have these computers lying around, and yeah, why not use them?
Mm-hmm.
So that's good.
Yeah, one of the easy ways to scale a build is to get a faster computer.
Mm-hmm.
And I know you have a fast computer, and I have I think it's a 12-core AMD computer.
Mm-hmm.
So that's 24 virtual cores.
Mm-hmm.
And these systems are really fast, and they're for parallel stuff anyway.
Yeah.
And they're really cost effective. I think I built mine for like $1,000 or something. So,
Yeah.
when you look at your time you spend waiting for stuff, building a workstation designed to build stuff is well worth the money oftentimes.
Yeah, that's well said. Yeah, actually, I think you really don't have to go and buy like a 250,000 blade server,
Mm-hmm.
right? But a decent system goes a long way, and I think as a developer, depending on what you do, that might be a very good investment. Um, and if you kind of like put together an upgradable system, it can kind of last you for many years, where you can just upgrade your storage, your memory, your CPU, and keep going, really.
Yeah, that's very true. I've run a number of motherboards through the case I have here, and it's pretty easy these days. I mean, you buy a motherboard, you slap it in there, and it just works.
Mm.
There aren't jumpers and all kinds of weird things you had to do in times past.
Mm.
But I would say one more thing about computers. You can buy laptops with like huge numbers of cores in them. But what I've been hearing from people is they typically throttle, so you can only get so much performance out of a laptop because you can only get so much heat out of it.
Mm.
So buying a laptop with a huge i9 processor and 24 cores probably really won't get you as far as you think it will, because you can't get the heat out of a box that small.
Mm.
You really need a workstation with a nice big fan and heat sink and something designed to run that number of cores. So anyway, if you want a lot of cores and you want to go fast, you pretty much have to have a box, not a laptop.
Yeah, absolutely. Yeah, I think if you can kind of like put like liquid cooling over your CPU, and then put SSDs in there,
Mm-hmm.
your fan never kicks in. It's like silent killer.
Yeah.
And I'm really surprised, because I was wondering that it will generate a lot of fan noise and stuff like that.
Mm-hmm.
So desktops nowadays, they are very quiet, and so I agree. I think for serious builds, it might be worth looking at a desktop system with like good airflow and stuff like that.
Mm-hmm.
And I think you have to look at it. You're kind of iteratively spending time on it, right? So over a year, you might have saved hours and hours of work for yourself, and so you can do the economics of it, and it might turn out to be a good investment ahead of time.
Sure. And I find these workstations, they last a good while. I mean, I use them for 5 to 10 years, and they're still, if you have a large number of cores, it's still a very effective machine in 5 years.
Mm-hmm.
So
yeah, absolutely true. And I think if you keep them upgradable, they can last you a lot longer. So.
Mm-hmm.
Sometimes if you plan a little bit ahead of time, that might really keep you like at cutting edge for many years with like minimal investment.
Mm-hmm.
So I think say if you kind of optimized your hardware offering, because there is money involved in there. You want to take advantage of all your software technologies that you could do, and so we were talking about all these parallel compiles and distributed compiles and things like that. And over a period of time, I think, we were mainly talking about like C++ build systems, and, we found that when applications started growing bigger, right, like browsers and others, um, you could do all these technologies, but then the time you spent during linking was kind of like coming to be the bottleneck.
Sure. You might spend
So,
10 minutes doing that, huh?
yeah. So, and that became important because, say, you did a modification in a single. So let's say you spent all your time building your browser and everything is great, and of course, like the incremental builds are bread and butter. Like, so you should definitely have a build system that can do incremental builds. So I assume that most of them, they are good at that nowadays, whether it is CMake or Meson or others. So I wouldn't worry about that. But the real linking will still happen.
Mm-hmm.
So now your loop is what, like compiling one file maybe takes you a few seconds, but then linking takes you like 10 minutes, right? And that's after linking, you're now able to test whatever you're doing. So your edit, compile, debug cycle is now 11 minutes or whatever it is. So it'll be good to cut down on your linking time and then go, you know, do that. So a lot of times people use shared libraries, that helps with this because then you're just building one shared library, not the whole thing. But even the shared libraries, in some cases, they may be big. And I mean, I'm again looking at WebKit and others. They may be linked in as libraries, but then they are like huge libraries, huge shared libraries. So there was a project called Gold, that was started, and one of the problem with talking about GCC toolchain here was that the linker was single-threaded, and that's fine because single threading makes it easy. You're reading the objects in, you're resolving the symbols, and then you do another pass for remaining symbols, and you're done. It's good, and you don't miss anything, and your tool is simple. But then when you have huge binaries to link, then this could be a problem because that's what it's doing at the very end. So Gold tried to be multi-threaded, and it was kind of a project that was primarily developed by Google, I believe, but it was kind of added to binaurals and contributed to the GCC toolchain. And earlier, it was touted to be a replacement for the traditional linker that was there, but the linker has a linker script, right? That you can design what to put where. And the GNU linker had like that script to be very, what do you call, programmable, right? So a lot of embedded systems, others, they started using that to, do things with how they want to lay out their binaries. And Gold could never catch that, right? So there were like a lot of places when you switched Gold as your linker and things would break because it wouldn't do the things that the linker did in the past with their linking scripts. And so it became like a good tool for doing a single application links, like say linking the browser and things like that, which is still good. So you can have your whole system built with how you are doing. But then, the applications which really are large C++ projects, you could use Gold linker. And that really speed up your linking for large C++ applications because of its multi-threaded nature. And there are more tools now. There's a LLD, which is a LLVM project. That's even faster. And I think there is another linker out there. I'm not getting its name right now, but that's even the numbers look that's probably the fastest linker out there, which kind of like shows linking the browser in like a few seconds and things like that. Some crazy number.
Yeah.
So we are down from like 10 minutes of link to less than a minute link. It is a great progress.
So in a Yocto build, what percentage of the build uses the gold linker or some advanced linker versus the standard linker?
So in Yocto, you can choose.
Mm-hmm.
So in Yocto, where it is known that it won't link with gold linker, the recipes, they basically force the linker to be the traditional linker,
Mm-hmm.
right? So it will demand that I want the BFD linker. And then in some cases, it might demand gold linker, but I haven't seen that so much often. But some packages, they probe your system for, hey, do you have a gold linker? If you do, then it will use the gold linker.
Okay.
So if you choose gold to be your distro linker, right, then I think, except few packages, everything else would be able to link with gold.
Mm-hmm.
I don't have number, but it could be as high as handful of applications not using gold linker, but then everything else uses gold linker.
Sure.
And then LLD is another one, which if you are using Clang and compiler, then LLD is an option which is kind of in the same footsteps as gold.
So in the Yo builds, you would enable LLD as the default linker?
Yes.
Yeah, very good.
Yeah.
Okay.
I would think that as a default linking, at least for larger applications, that would make sense. So you would basically want to use LLDS.
Mm-hmm.
And you might not see, so even the traditional linker has gotten better now. So I think, gold came out like maybe 10, 12 years ago, or even longer probably. When it started to work, things have changed, in ever since, even in the BFD linker side. So it's probably not as bad. But if you kind of like are working in just say in a browser space and things like that, then it's better to make a choice yourself.
Sure.
For your application, and not really rely on what the system is offering you as a default linker, system linker option.
Yeah, it's a good thing to be aware of. And another example where we try to, in the Yo distribution, we try to set good defaults that are the best developer experience and the best OS that we can deliver at this particular point in time.
True, yeah. So for example, if you build Chromium with your distro, it's going to use Clang with LLD,
mm-hmm.
right, underneath. So you would see that is the default, and you really don't have to do anything for that to happen. So yeah, so we try to keep like our default options, which are sane and simple and fast and optimal.
Okay. So while we're talking about Yocto, what are some other things that Yocto does to speed up builds?
Yeah, so Yocto has this concept of shared state or sstate. You might have read about it on mailing lists or other places. And so shared state essentially is a snapshot of your build directory for a particular component. So we talked about how Linux systems are put together. Every package is built on its own. And shared state basically takes a snapshot of its build and then puts it together with some metadata around it. And it does that for every package that it is building. And then it puts that into a store. And when you do a rebuild, now it basically does some checksumming and some calculation of hashes, and and then it searches those hashes in the store, and if it finds a hash match, then that object is used. So it might be that you're building your image, right, and you didn't make a change, and you are basically having shared state from a server or somewhere, like a feed of shared state. It might not build even a single thing.
Mm-hmm.
right? It might pull all those pre-built objects from the shared state, populate that in your local workspace, and then give the image out to you. So the so that's basically the high level what sstate is. There's a lot underneath it. It's a very complex piece of software in the Yocto tooling space. But what you see is that when you build with Yocto, it creates this shared state folder, and as it builds, it's also taking those objects and putting that into that store. And it's also making sure that when you do a rebuild, then you can reuse a lot of what you have built previously. And it's very fast from that point of view. When you're really building full systems, then this technology really helps, because most of the time, if say you are in a setup where you have an auto builder or something where shared state can be generated overnight or whatever, and then everybody all their development team can then consume that shared state, then you're really accelerating them, because then obviously they're not building the whole system. We were talking at the start of our conversation about build times, so they have a good offset with that.
Yeah, so if one developer has shared state, or if you have a common shared state, to set up a new build, you just copy the shared state directory over, and then you can do a build in 5 minutes. So, yeah,
pretty much. Yeah, I mean, shared state has a mechanism to set up as a feed server, like your RPM feeds or dev feeds, but you really don't need even that kind of a complex structure. You can just kind of share your sstate folder, and that should be enough.
Okay.
And it's kind of a fallback mechanism there. So if it doesn't find it, it will still go and rebuild it. So your builds won't break, but if it finds some matches, then it won't rebuild those. So that's awesome.
Yeah. What would be kind of cool is like a global shared state where every Yocto developer could, kind of like Nix, where it would pull down the package if it found it somewhere on the internet.
Yeah. You need like a single source of truth for that. So in the sense that, or a mechanism where I could inject my sstate, you could inject your sstate into a common space, or maybe I could expose my sstate in a Web3 way.
Yeah.
Where if the third person is building, then their build system is able to access my sstate and your sstate that we decided to expose, and then build a fused view. And then internet is fast, that it can suck in those megabytes of data within no time into the local sstate of that person. That would be awesome.
Yeah. So is the actual data stored in SQLite, or is it stored outside of SQLite and the database just provides an index?
Database just provides an index.
Yeah. Okay. So there'll be a bunch of blobs of data in your shared state directory, right?
Yeah.
Okay.
And I think there's a tool to which you can run on that shared state folder, which basically keeps it refreshed. So because what happens is when you're like incrementally building over day in, day out, the shared state size may grow quite a bit. And these tools help you to like discard some of the objects that hasn't been used, so there are different policies you can choose to discard. And so there's a sstate cache management tool also that's up there. You can run that tool, on your workspace. But if you're like building few projects, and you have like 1 terabyte of hard drive, I wouldn't bother doing that.
Sure, right. You just clean your directory occasionally and start from scratch.
Yeah. So I think that's actually a very powerful thing. In fact, the sstate is very reliable actually in Yocto. I mean, on and off you'll see some issues pop up here and there, but mostly it's always like a reliable store. You really don't notice it.
Yeah. So that covers C++ and Yocto, and one of the emphasis we see in some of the new languages like Go and Elm.
So this is something I'll ask you, because I think, you've been basically involved in a lot of these more modern languages, and I would also include Rust in that, the C++ gang, because maybe it's because of the memory checker and that, sort of stuff, but still, like, the Rust builds are slow, right? They are not very, very fast. And I think you could argue that, you are basically borrowing the time that you would otherwise spend on runtime garbage collection, right? And you're doing that statically. So, and then if your application runs for, days and years, then, how many times garbage collection is invoked. So you can like do some proration of that time, but that's separate. From a developer's point of view, it is slow, right? Now, so I'm pretty sure that, that a lot of languages, they move to this new paradigms. And I think I'm hearing a lot of this, that the build times are really blazing fast. So I know that you've done stuff with Elm and Go and also like NPM and other things. So what's your take on like this, how it works? What are like your learnings from Go Elm?
Yeah, so Go and Elm, I work with those languages a lot in the Simple IoT project. And we ended up with those languages because they reflected the values of the Simple IoT project in itself, in that they're simple and effective. And so one way to speed up your build is to use a new language like this. And I don't know where Zig stands, but maybe it will be fast too. I don't really know, but it seems like their values would be similar. So what Go and Elm have done is they've purposefully kept the language very simple, and they resist adding features, or they're very slow at adding features. And what you have with a simple language is you can parse it very quickly, and there's other features like in Go you can't have circular dependencies, so they force you to keep your code clean to some extent. And then the compiler has built-in knowledge of the build tool. Everything's built into the build tool, so there's no separate make tool or other caching tools that are needed, because the build tool itself is very intimately aware of the language. It knows what needs rebuilt and what doesn't. You don't need an external tool to do that. The build tool does it itself. So it's not uncommon for pretty large applications to have build times in the range of a second or two, or even less.
Wow.
So with both Go and Elm, I always have a process set up that's watching my code and recompiling as it changes. Go has a built-in unit testing framework, which is, again, it only tests what changes, so it's very intelligent, seeing what changed. And with Elm, it's very nice because you can use Elm Watch to see your changes in real time as you're writing code. And again, the build is so fast that you can just type, boom, you see your change, you can tweak it. And for UI development, the fast builds in Elm are really nice. And ironically, it's Elm is a compiler. It compiles to JavaScript, but it's generally faster than any of the JavaScript solutions out there that do, the bundlers like Parcel or the bundlers that take big gobs of JavaScript and put it all together.
Yeah.
So anyway, that's my experience. It's really nice, and sometimes I feel like you just need to start over.
Yeah.
Take what you've learned and
So do you see any similarities or any advantages of the managed module systems, the ecosystems that these languages have? Because you have a lot of modules, right? So nowadays you start off and then you start pulling in those modules one by another and bring them in. So do you see any advantage of that kind of a system for kind of like build acceleration as well, or is that just something not uh, an advantage?
Yeah, at least in the Go space, you pull it in, it gets compiled once, and then it's done. It never touches it again. And that's cached in like a global area for your user account. So you can even have multiple Go projects, and if they pull in the same version of a Go module, it'll just be there ready to use.
Just like a Nix store then.
Yeah, exactly, your own personal. And I read recently that the Go language used to deliver part of the runtime compiled, but they're no longer even doing that now. And so the download size for installing Go is smaller. And as soon as you need something, it builds that piece, and then it's there, it's done. So
yeah. So I think it's I know that like a lot of times developers, they have this set of tools that they work through, and I think traditionally with C and C++, it has kind of like you go from one to another, and like you have all these things, they line up your workflow. And with Go and Elm, do you see that there is a homogeneity in there, that you have like all these tools under one umbrella, and then that helps the whole process and accelerates your build loop?
Yeah, not as much, because again, the compiler and the build tool is built into the language. So generally you don't need anything else to get a basic build.
Okay.
So where we see most of the work in tooling in the Go and Elm ecosystem is around CI and static checking, and just a whole raft of really nice tools that really make your code nice. Both the Go and the Elm ecosystems have very advanced tools for ensuring code quality. So what I've seen in these systems is, people aren't spending any time on build time because it's a problem that's mostly solved. So the tooling efforts are all focused on improving quality beyond build time.
I see. Yeah, that's a good point. And I think what I hear you say is that it's about reuse and not rebuild.
Yeah.
And I guess, if you look from traditionally, people use like distributions like Gentoo and others, where like you compile it locally, and nowadays I think it's more like move to. I mean, Gentoo is still around, but there are distributions like Arch and all, which basically offers you pre-built packages for a traditional Linux distribution mechanism style. And I guess that's what I'm hearing you say is a kind of an inbuilt into the Go ecosystem.
Right, exactly.
Cool. So so I think there is also one aspect. I'm kind of like talking about build systems here, and we did touch base on what the recommendations should be for building your build machine. But a lot of times, people kind of start doing Yocto builds, and then they run into this build problems or issues. One of the things that Yocto does is, it builds. So there's your package parallelism, right? So you're compiling the thing in, say, make minus J16, right? And you said, I have 8 cores, make minus J16, great, right? But Yocto has another kind of a dimension to parallelism, which is packages. So it basically divides them into various tasks. So you may have your image consisting of 100 packages. So it builds a tree for how to sequence these 100 packages in parallel. And then starts building from the leaf side. So now what happens is, it could be that if you said, give me a parallelism of J16 and give me a task parallelism of 16, right? So that means it could be running 16 different tasks at a given point of time. And it could be all 16 tasks are compiled tasks.
So are you telling me this is 16 times 16?
Exactly. So now, that's how many parallel compile jobs are running, right?
Yeah.
And obviously you are going to get ooms and whatnot. And a lot of times those error messages are not very, very clear unless you really look into your core dump CTL or something like that. Hey, what dumped the core? Or, did ooms got triggered in and did it kill some things? And
so means out of memory handler in the Linux kernel, where the kernel just starts killing processes that are using gobs of memory. Yeah.
Thank you. Yes. And so I've come to this, general maths that I usually find, useful with especially with Yocto wheels, is that, say, you got a machine, right? It has 4 cores, right? Then minimum you should have 16 gig of RAM. So you can keep multiplying. And so 4 gig per core is actually something that will never get into this situation where, the ooms killer comes in and starts kind of, knocking off your bills. And if you don't do that, the other option is to tweak your build parameters. So actually there is some work that has gone into BitBake now, which basically is sensitive to the system pressure nowadays. But I'm not sure whether it has made into a release yet, but maybe it made it into the last release. But that's basically trying to use some of the Linux tooling or Linux infrastructure underneath to find out how the system is doing, and it won't issue a new job until the pressure falls below a certain limit and things like that. So it might get better with that in future, but again, I think you want to build a machine for the job. Then general recommendation around that is have 4 gig of memory available per core.
Yeah. So it doesn't make any sense to buy a 32 core machine and only have 32 gig of RAM, because you'll exhaust RAM before you. Yeah.
Yep. Yeah. Exactly. In that case, I think you basically limit your parallelism to minus J4 or something like that, or J8, something like that.
Yeah. Okay. Well, that's good to know. We'll definitely put that in the show notes. So anything else yet you want to share about this?
Yeah. I think that's all for today. I can talk about these topics day in, day out. And so if there are other interesting aspects that we would like us to explore, please provide your feedback, and we'll be happy to research that and provide you more readouts on those. So thank you very much.
Yeah, thank you, and till next time.